So we've listened to 5 speakers with their presentations, and we have 2 more presentations left.
Now, next 2 speakers from through online presentations. I hope first speaker is the Florian LENZ. He's a technical director from CEVOTEC, German. I hope he's connected.
So the last 2 presentations will be done online, so it might not be easy to receive questions because the presentations are done online. Okay, I think we have Mr. Florian LENZ online.
That is correct.
I think we are connected.
Hello. Florian, who will give us a talk on the H2 tank reinforcement yielding 15% weight and cost improvement. Thank you so much for giving us a chance to listen to your experience. Are you ready to present?
I am ready. Thank you very much for the introduction.
Thank you so much, and please go ahead.
So, I hope you are able to see my presentation.
Yes.
Perfect. Thank you very much for the introduction and also for the opportunity to present technical developments done by CEVOTEC and other partners in the field of pressure tank reinforcement with the use of FBP placement technology. I'm myself our technical director of CEVOTEC and head of the development in this area. As the motivation behind H2 tank development, I think we all agree that we are entering an age of electric powered mobility. And of course, there's as we also learned in the last presentation, there's a discussion and also a competition between different energy storage systems. And as it looks today, battery storage, especially for passenger vehicles, is currently in the lead. But we see and also believe that in the end, there will be a mix that H2 economy and H2 systems will have their market share, especially in truck and lorry, or let's say larger mobility applications, trucks, lorries, possibly railway, and also aerospace, where all the advantages of H2 compared to batteries can be utilized. So here it's really a rough overview of the different storage systems. I think the auditorium, basically, you are familiar with different items. There's basically the high pressure storage and cryogenic storage, of course. And especially for land-bound transportation, we see the pressure and the high pressure storage as the most relevant, at usually 700 bars. And for H2 overall, there's growth predicted, and as I said, also our belief that we will see this growth as depicted on the right-hand side, as countries in Europe, but especially Asia, and of course, notably or also perceived in Europe this way, Korea is one of the potentially and actually leading countries in this respect. So, but also Germany aims to expand the H2 economy. So I do see a strong possibility for cooperation here. And overall, the market share will grow, and we think it will proliferate also in, let's say, smaller and smaller cars, or even having a mix in the end. But driver for this, of course, is overall to be seen, aside other issues, H2 procurement and so on. It's of course the storage, and this is what I want to talk about today. The storage system cost is a key driver and has already been reduced in the last decade, notably around about 25%. But still, there's room for improvement, of course, in the competition with other energy storage systems. And within this costs that are still remaining, the use of carbon fiber in those storage systems is the biggest single item, with more than 50% of overall cost. So this is exactly where we see a angle angle for improvement. To understand what we're exactly aiming for, or what our concept is, let's have first a look at typical buildup of a pressure vessel. It usually consists of three principal orientations. We have the low angle helical winding, low angle helical layers, which are holding together the liner on the ends, more or less. The hoop layers, which are wound around the liner to prevent bursting, and high angle helical layers to take in stresses on the dome area that the low angle helical winding cannot take in. So on the above picture, you can see the typical setting, and blue are the high angle helical layers. The thing is, those reinforcements are actually only or mostly needed only at the dome areas. So in all the cylindrical area, they are more or less dead weight, or not well used material or not well used expensive material, as we discussed. So we propose, and okay, this was already proposed some years ago, for example, by the Department of Energy in the US. So the overall idea is not new, saying let's focus on the dome reinforcements on the end. That's the green one in the lower picture, and save the high angle helical layers in the cylindrical section. This enables us first to save material, and second also to gain space, storage capacity. If the outer diameter is fixed and we are thinner from the wall's thickness, we get more storage capacity. And this only can, and this is where we come in, I'd say, because this concept was or is known for several years now and has already been proven generally to work, but until now there's a industrial way of transferring this concept into practice missing, and this is where we come in and do our development. And you can see on the left-hand side a concept of a system that CEVOTEC is working on to provide. This is doing the so-called FPP patching. I will explain both later on a little bit more in detail. But basically, it's an automated way to put down this reinforcement. The first time globally, this can be done in a fully automated process. And then the liner can be transferred to the classical manufacturing of filament winding. Schematically depicted on the right-hand side. So this whole equipment on the right-hand side is for the manufacturers, it's already there. They use it right now. They can still use it. Just the liner itself that's put into filament winding manufacturing is locally reinforced, as you see with the green areas on the domes. To give you an insight of how this can play out in a industrial setting, so in an economical setting, we have conducted a business case study based on realistic and real data provided to us by partners. And I will show you this rather briefly to highlight the potential that's in there for a more competitive H2 storage system. The case study was done with a vessel that's 1.7 meters long and roughly 400 millimeters in diameter. So from the size, let's say a rather small truck vessel possibly. They can go up to 2.5, 3 meters even, and even the diameter can be bigger, but this is, let's say, a medium-sized lorry storage vessel. I won't go into all the details, it's just for overall description. In the end, we do have an overall mass of carbon fiber composite of roughly 75 kilograms. And this mass consists of those three principal orientation direction I talked about. It's in the pie chart below. And 20% are those high angle helical layers, 14 layers, which can be mostly replaced. Some of it not, or the hoop layers, for example, have to be a little bit thicker, but they are used in full, so we can save part of those 20%. And as a little spoiler up front, I will tell you that we will be able to save over 16%. So out of the 20 potential, we utilize roughly 16%. That is equivalent to more than 12 kilograms of carbon fiber material. So it's a very, very direct impact on the whole manufacturing in the end cost. But it has other effects too, and this is what I want to elaborate in later slides. So we'll show you what else this has impact on. But first, let's have a look how we reach, we have the setting, we have this geometry, how do we reach a part, a component, a vessel design that's manufacturable. And here we do have a workflow combined with our FPP systems. It's based on a CADCAM software that enables an import of CAD geometry of the liner that you as a manufacturer will have. We can then decide in a completely virtual workflow, assign orientations. We'll have guide curves for our process. This is the lines in which our reinforcement strips, so we call patches, are placed. The laminate is designed in a virtual way, and we can of course also do all the combined or the possibilities of virtual design, make quality checks, thickness distribution, export that to FEA simulation, the layout that we do. And as a next step, we first virtually test, or from this set, if everything is fine from a technical standpoint, we can then export machine data and do an offline robot programming, and also simulate the manufacturing itself with a digital twin, also to prevent any collisions, for example, of the robots and so on. So this is fully integrated into the software environment. And on the last video down below, you can see a exemplary manufacturing in a manufacturing cell that we have in our lab that is very variable for different applications. So for those of you not familiar with the FPP process, this was developed several years ago by Airbus actually, but is now put into industrial roadmap by CEVOTEC. And it basically consists of a cutting of fiber material, for example, pre-preg in this case, a quality assurance based on a vision system, then a pickup, again, a control by a vision system to make sure that the alignment of the patch is ideal, and then the putting down of the patch on a tool that is manipulated, for example, by another robot. And you know, the access and manipulation options can be varied, of course. And one integral part that we are working on is the gripper technology that enables the picking and placing of those patches without, for example, any debulking steps afterwards. So this is the general process setting. And if you now jump back again to the case study, it is the weight reduction of roughly 16% that I've shown, leading to a cost reduction of 14%, because we of course have some machine invest, some depreciation. So this means the cost is a little bit, or cost saving is a little bit less, but still very attractive, we think. And also very important, and we see this all the time in FPP usage, the overall process time of a combined process, FPP plus winding, goes down 19%. This means we can, an existing winding line can have 20%, almost 20% more throughput. So with the same equipment, you can manufacture 20% more vessels. In respect to the time, I won't go much into detail about different aspects. So very generally, of course, material costs mostly go down. Depreciation is a bit higher for the equipment that we provide, but overall, the saving of roughly 14-15% is there. And also very quickly, the investment figures with roughly 10 million euros of investment, having a MPV of 69 millions and a IRR of 111%, with a payback of 12 months. Those are all very good values, of course. So we would, of course, be happy if you are interested adapting this to a concrete business case that might be in your company. But here, for the settings that we chose, we already have a very attractive option. Thinking about 30,000 vessels to be produced. So very briefly, what is the technology status here? Also to show you the history and where we are from a maturity standpoint. 2019, so 2.5 years ago, we started with the development. We made a proof of concept just of, let's say, manufacturing and geometric aspects. In 2020, there were full-scale manufacturing tests done with, as you see, rather smaller pressure vessels, which were successfully bursted. So this was the first hard fact proof of technology working. And then in 2021, there was this still scaled demonstrator of a larger vessel. So put down here, or actually this is just a schematic or an own build example. The actual part with roughly the same geometry is, of course, from a partner and strictly NDA protected. And what we are working on right now, and also proving and want to finish this year, is the industrial concept for the machine that I already have shown a bit. And we see next year as ready for the general launch. Already working on the development project with partners, testing the technology with our lab equipment, But of course, planning on next year, if everything is successful, what we as we think it will be, then next year will be the way to promote this further. And yeah, to see how those modules that were briefly shown of a FPP system will look like for a pressure vessel application. Here is the concept of our PV system, and this is basically consisting of the same modules that we usually see in for other FPP systems as well, adapted for the cause, of course, of patching pressure vessel composite pressure vessels. So here we have the material feeding in the back on a spool put in here. Material cutting can be done by laser. This is our lab equipment, but also ultrasonic cutting, which is more better for prepregs. We have already all tested and put into commercial systems. Then the first vision system inspecting the overall quality of the patch, and then of course the belt that's putting those patches, those strips forward for robots to pick them up. Two of them on rails to allow for variable size of the vessels. And yeah, okay, here is also the second vision system you see here from below, that's inspecting the patch on the gripper before placement, so tight quality control in all steps. Additional is this this additional axis will handle the liner, of course turn it while both robots at the same time patch the ends to enable this positive business case that I've shown. So this will be the setting, or with some changes. As I said, it's a concept. We are currently working on a quotable and realize, or a system that we do want to realize starting next year. Will be finished even in this year, and then to move forward with our industrial partners. And in this setting, just to sum it up, of course, the core of our know-how and our work is providing a system for FPP reinforcement. We call it Samba series, so this will be Samba pressure vessel. We do have already tried and tested the software surrounding to enable a quick integration of FPP into existing workflows, CADCAM workflows. And upfront, maybe for feasibility studies and so on, we do have the CEVOLab, the FPP competence center, as we call it, to test upfront before, of course, investing into a machine like this. This is generally our way forward. Thank you very much again for the opportunity to present this. Feel very free to contact me. I would be happy to receive some contacts from Korea. As I stated in front, I do believe that in Europe, especially Germany and Korea, can have a lot in common here. Progressing H2. So yeah, thank you, and possibly questions or contact later on. Thank you very much.
Well, thank you so much. It's a very interesting technology. I agree with you. You can save about 15% of mass and cost. You are still with us? 지금 제 진행에 그 질문을 못 받는 줄 알았는데 질문을 받을 수 있는 것 같아요. 그래서 질문이 혹시 있으시면은
I think we can receive questions. So if you have any questions, you can say it in English or Korean, and we will try to receive any questions if there are right now.
Well, I have one quick comment. So using your dome reinforcement, I think that is more effective in longer cylinder because in longer cylinder, the main part of a cylinder, the carbon fiber is mainly determined by helical to enforce the dome part. But using your technology, we can better optimize the layers in cylindrical part. Is that correct?
This is basically correct. So what you said, like on longer cylinders, there's even more to be saved. While, for example, a spherical pressure vessel, there would not be any use at all, right? So the longer they get, the more interesting it becomes. And of course, because we are very free with the angles. Usually with winding, you are limited to geodesic lines by the process. And we are very free to place the reinforcements. So you get an extra benefit ability to optimize there. Or you could also, of course, if you have attachment points or something in the vessel itself, you can also use it in the overall area of the vessel. So you have an extra design freedom here. That's correct.
예, 제가 그 질문을 드린 이유가
The reason why I
실린더가
asked
이제
that question is because if the cylinder is long, then the cylinder part, the fiber, because we have to get it from the dome part, so we could waste the use of fiber. And if we use this technology, the FPP technology, then we can separate the dome and cylinder and we can reduce the mass of the cylinder more effectively. And I think Mr. Florian also agrees to that.
In placing, your robot will pick and place the carbon prepreg over the dome, but dome area has a certain curvature. So when you layer, robot layer, you have to change the robot arm to fit that curvature. Am I right?
This is done. Thank you for the question. This is done completely automatically. So if let's say the gripper itself, as you have seen in the video, can accommodate for curvature, right? So it can put down the patch on a curved surface. So this is no problem. If we have to reach another area, then for example the manipulator has to move the tool for the robot to reach this area. So we don't have to change the robots. We have to change robot position a bit, but this is completely automized, of course.
예, 저도 이제 복합 재료로 용기를
So I'm someone who is also developing vessels using composite materials, but I think that this idea is a very good idea because mostly before Korean companies has been doing toe preg winding, and so I think we can apply this technology to our conventional methods. So if we use the FPP technology, I think it will be a good technology to adopt.
Well, okay. So thank you so much, Florence. We hope to see you physically in Korea someday.
I will be very happy to visit. Thank you.
Okay. Thank you. 예, 박수 좀 부탁드리겠습니다.
Let's give him a big round of applause. Thank you very much.
Next speaker is from CEVOTEC.